Great, so this is lecture 11, where we continue and hopefully finally prove Stein's theorem for the spherical maximal function. So previously, we saw that we had this L2 Sobolev inequality, which was, why is it called a Sobolev inequality? It's because I'm relating some L infinity norm to L2 norms, and I can control this L infinity norm by those two L2 norms, right? And one of which is incorporates the derivative of my function. So Bourgain did this. Probably, I mean, everyone did this that has done maximal functions, but we're going to use a formulation due to Bourgain, where he introduced these parameters, which I'll call alpha j and beta j. I think there's the same notation he used. And what we do is we start with some function, k, and k is for kernel. I'm going to be taking a convolution with it in a moment down here. For the moment, I'm just going to assume that the Fourier transform is in C1, is C1. If it comes up, I ended up needing more derivatives, by all means assume it. But the real reason for the C1 is the appearance of this gradient right here. Okay, so I am going to define alpha j as I look at the supremum of the Fourier transform of k in this annulus, where I go from 2 to the j minus 1 up to 2 to the j plus 2. Normally, you'll see this as 2 to the j to 2 to the j plus 1, but because of my smooth Littlewood Paley projection operators, it's a little bit fatter. It contains the adjacent ones. And v to j is the same thing, but where I've incorporated the gradient, and it's getting interproducted with the directions c. Right? And so our L2 bound is the following. If I look at the maximal function, where I take as my average, my starting average, my say T1 would be of f is going to be f convolved with, oh, not that, pj of k. And then this dilation thing right here is actually, TR is defined by those isotropic dilations. That is how you get all of these right here. So when I do that, when I look at that maximal function and I try and bound it in L2, it's actually bounded by the alpha j and the beta j. And this right here is actually where the loss of a derivative comes in. Remember, this v to j is measuring the derivative of my kernel, or its Fourier transform at least, and it makes an appearance right here. And we actually say usually it's lost half a derivative because I take this power, this half power right there. Okay. Now you can imagine that this is going to make use of that Sobolev inequality to prove it. But before I get to the proof, let's actually just quickly record what this would mean for the spherical averages. All right. Well, what are the alpha j and the beta j's? Let's recall the bounds we have for the spherical measure. Its Fourier transform decays like this, and it's the gradient of its Fourier transform decays like this. So that means my alpha j is actually just 2 to the j 1 minus d over 2, and v to j is similar. It's 2 to the j times 3 minus d over 2. And when you compute what those terms are, it turns out that you get 2 to the j 1 minus d over 2. And Bourgain's lemma now says that if I look at just this Sj of r, I don't look at the full high piece yet. I just look at a single Littlewood Paley projection of that spherical average. Then I get a bound, I get this times the L2 norm of my function. And now you just sum up over all j, right? I can use the fact that SR high of f is less than or equal to the sum over, and I should have said, before I said S low was not, I may have mistakenly said this, like, whatever. I want it to be less than or equal to j. I may have accidentally had a little j there. So yeah, so I just apply the triangle inequality in a blunt way. This SJR of F, and or at least in L2. And you just get to sum up these bounds. And since that is 2 to the j and it's the smallest j is big J, you get that bound. And so what this tells us is that on L2, the high frequency piece of the spherical maximal function has a lot of cancellation, and you see this manifested in the L2 norm. Okay. Now we would like to say take j to minus infinity so that we could recover the whole function, right? Or the whole operator, spherical averages. But this operator norm blows up as you take j to minus infinity. So it's not good for us. Okay. Anyways, let's go on to the proof. Whew. All right, so we had this reduction to the dyadic maximal function, where I just take reduction to a soup between 1 and 2, right? I had this saying that if I know that this is bounded on L2, then that implied the soup over all positive R is bounded on L2. It's only a loss of a factor of 3. All right, so I'm going to use that, and this I get to apply this because my conditions were assuming that k is frequency localized to 2 to the j minus 1 to 2 to the j plus 1. Cool, I get to do that. And great, so let's also use one of the techniques that came in here, which is sort of the self-reproduction, or the Calderon self-reproducing aspect. So to do that, we can actually get that. So first off, we're only caring about this now. And we also are going to use the fact that if I take F, and I convolve it with this is going to be equal to huge A of F. Convolve with the same thing. We get in this extra little Paley projection by the same reasoning as before. If I just look at the Fourier transform of this, of both sides, then this QJ is multiplying by 1 in the appropriate region. Okay, and there's a J here and not like a shift like J plus K because I've just reduced to this range of radii. Okay, and just to remind you, in case you've forgotten, QJ was defined as, let's make that look better. QJ was defined as the sum of these 3 little Paley pieces. Great. And now, okay, I've got that, but how do I bring in the Sobolev inequality? Well, the way I'm going to do that is I'm going to introduce a function, big F of Rx, and I'll define it as just this right here. I don't know why I drew it like that. I can make this look a lot better. We're just saying I define this to be f r of x. So that 1D Sobolev embedding theorem said that the sup over r between 1 and 2 of fr of x, which is the supremum, just brings us back to a function of x, where x is an RD. So that is less than or equal to, well, L to the minus 1/2 the L2. Let's make this clear. Plus L to the 1/2 the derivative, right? With respect to r. And what is I here? Well, I will simply be the range of r that I care about, the range between 1 and 2. And L is going to be something we optimize later. It's clearly going to have to relate to the alpha j's and the beta j's. And so that's going to be the point now on. Just to be clear, these two L2 norms are just doing an L2 norm in this variable here that I've not written in. I'm not taking an L2 norm with respect to x. Okay, we'll have to do that later on. And how do you do that then? Well, if I take this sup over r and I, fr, well, if I do actually take the L2 norm in both, oops, I don't want it in R, I just want it in X. Then this is less than or equal to, well, I take the L2 norm of this whole thing in terms of X and this whole thing in terms of X. The factors of L don't impact that L2 norm. And instead you just get the L2 norm of F on I cross RD times L to the minus 1/2 plus L to the 1/2, the L2 norm of this, also on I cross RD. Great. So now we better figure out what these things look like. And the way we're going to do that is just apply Plancherel's theorem.
So wait, just a question. You could choose, if you wanted to though, you could choose L to depend on X, right?
Could choose L to, yeah, I could. That's
probably not important. I was just.
No, I'm not seeing anyone do that.
Yeah, I mean, you couldn't do this last step if you did that, but.
No, but I mean, maybe you have some other, you could maybe rig up some other scheme to handle that. That's an interesting idea. I do not know how to proceed off the top of my head.
Okay, sorry.
With that, but
I'm just spitballing.
No, it's interesting. Yeah. Okay. Let's apply Plancherel's theorem now. And so this is actually the Fourier transform of L2 of I cross RD. And I'm going to write RD twiddle. I'm just doing the Fourier transform in the X variable here. I'm not doing it in the R variable. And similarly on the other side. So I'm taking the Fourier transform of the derivative of f, but only in the x variable. All right. And now we really need to understand what the Fourier transform of this two-parameter function is in terms of just the x variable and this one as well. It turns out the first one is actually pretty easy. So yeah, let's look at f. Right, so that is by definition the integral of f of r x, this is on rd, e of x dot c dx. Right, but fr of x is actually qj f, the integral over rd, qj f involved with this appropriate dilation, pj k, at x, and that's times e of x dot c dx. And so when I do the Fourier transform, it turns convolution into multiplication. And so we just get qj, the Fourier transform of qj of f, xc, times usual multiplication, the Fourier transform of this dilated projected kernel. All right. Well, this, remember, has the effect of qj is basically phi of c over 2 to the j plus 2 minus phi of c over 2 to the j minus 1. Yeah, that's the Fourier multiplier. So that's this is on actually equal to this. And so we actually only care about the value of this when c is in that annulus, right? The annulus being the annulus being 2 to the j minus 1 less than or equal to c, so equal to 2 to the j plus 3. There should be a 3 here.
No, I think that should still be a 2.
No, I had plus 2. Wait, where is it? Sorry. I had a plus 2 here, and it goes up 1 more. The way I define these things. Each phi was defined as 1 on the ball of radius 1 and supported the ball of radius 2.
Yeah, so I agree with you.
Oh, right, yeah, sorry. So there's a 2 here. Yes, okay, yeah, thank you. Good catch. But this is a 3 here. Great, okay. Yes, so our study now is, of course, this. And, well, this is where our Fourier transform property is useful. We said that the Fourier transform with the dilation in L1 was the same as, so this is dilating first and then taking the Fourier transform, is the same as Fourier transforming first and then dilating, but in L infinity at the inverse scale. So this is actually equal to that xc, which is of course just p, j, k, r times c, Fourier transform there. And this this picks out the same thing as this, but with a j over here and a j plus 1 over there. But this factor of r can push us forward a little bit. And hence, this is basically just, this is all less than or equal to alpha of j. And that's for all C and RD. And that means when we take the L2 norm, so this is on I and RD, right? Well, that's less than or equal to that's less than or equal to, yeah, alpha j times the L2 norm. Sorry, not the L2 norm. I get this QJ of F and L2. And then it's all this squared averaged over I square root. But that average isn't changing over I at all. So this is actually just an L2. Phew. All right, that was the first one. I guess, are there any more questions or comments before I go on to the second term? This term right here. It's a bit more complicated, but not too much so. Okay, I'll go on with it. So let's just write it down here. It's the L2 norm of the Fourier transform of a derivative. All right, so the L2 norm, the Fourier transform of the derivative that's what we want to compute, or we want to bound. All right. So yeah. So this is fun. This is where the dilations are going to be useful again. First, let's kind of try and figure out the inside right here. So the partial of R of F, I'll drop the R from notation. We just mean on the first coordinate now, okay? Well, what's this? This is a partial derivative on a convolution, right? And that convolution is F convolved with dilate by R, oops, that's a positive one, of your PJ of K. The derivative, you can move by linearity just onto that piece. So that's actually just F convolved with this. Oh, and that's of course at the point X. Great. Now we need to process this a bit further. Let's take the Fourier transform of this. Then I'm taking the Fourier transform and I'm getting it at C because I'm just doing it in the X variable. So skipping over the middle part, that turns that into the Fourier transform here, multiplication by that, XC. But I forgot, I actually meant this is QJ, remember? Yeah, that's how I defined it, FR of X. Okay, so now we need to do the Fourier transform of this thing. All right, again, we know how the Fourier transform, interacts with dilations, but we need to see how the derivative interacts with the Fourier transform. right? It turns out they actually commute because the Fourier transform is just acting on the x variable, whereas the derivative is just acting on the r variable. Okay, so this is actually equal to, or the Fourier transform of the derivative is actually equal to, so let me just maybe write that. Is just equal to the derivative of there. Okay. Oh, sorry. What was that? Let's do this. What I want to say is the Fourier transform of dr dilated, this projection kernel, the Fourier transform of that, xc, right? Well, this is equal to do the derivative afterwards. Okay. So now I need to compute the derivative of this. Phew. And how do we do that? Well, let's actually push the Fourier transform in first a little bit more. So by the dilations, this is of course, I dilate in the inverse scale in L infinity norm, the Fourier transform of Pj. Okay. These are all xc, xc. Yes. And now I could think about this as that. Phew. Okay. Are there any questions so far? I've not done much at the moment, but now it's going to take a little bit of thought. So right. So let's write this out a little bit. This is the partial of Pjk Fourier transformed of Rc, right? And it's with respect to this R variable. Well, if I have some smooth function, G, going from say Rd to R, then the derivative, delta R of these dilations are computed as follows. They're equal to the limit as h tends to 0, that's an h, of what? G R plus h times c, exact c, and minus g of arc divided by h. So I use the smoothness of g to bring out the gradient of g here. And that's going to be a gradient in the direction of c because that's fixed in this. So gradient in the direction of c of g, and evaluated at arc c. That's all times h. It's divided by h plus some O of, well, if G is smooth, something that is h squared depends on G, h squared over h, which is just O of h, and as h tends to 0, this term disappears. Of course, these h's cancel each other, and we actually just get that this is the gradient in the c direction of G R C. All right. Fair enough. We can write the gradient in the c direction as also just c, and are producted with the gradient of G at arc c. Yeah. All right. Now let's plug in G. of course, take G equal to, well, the Fourier transform of Pj of k, right? Which is itself psi j times the Fourier transform of k. Remember, psi j is this c over 2 to the j minus v of c over 2 to the j minus 1. All right, so I apply the gradient to this product. The gradient of G then is going to be, Leibniz rule, right? Gradient of psi times Fourier transform of k plus the psi j times the gradient of the Fourier transform of k. And therefore, this expression therefore the partial of r of the dilation by r inverse of infinity of psi j times k hat at the point c is just c times dilation by r inverse infinity, and I have k twiddle times the gradient of psi j plus psi j times the gradient of k twiddle. This is linear, right? So I can actually just write this with each part. Break it up into that sum. And now, okay, we see that the last summand, this part, that's going to give us the bound b to j. And by the same L2, the following of the L2 norms before, that'll give us a portion that is b to j again. Right, that's don't forget, that's because I've got this paired with c. However, this first part is not looking like alpha j. Okay, so I now need to go and look at c dot right here. Well, that gradient of psi j is actually going to pull out a factor of 2 to the j, to the minus j, sorry. In particular, what I'm saying is that I have the gradient of psi j, which remember, psi j is this thing right here. Well, that's going to be equal to 2 to the minus j times the gradient of psi 1 evaluated at c, evaluated at c over 2 to the j. And this is going to offset my c here, so that I get that c of this thing is an absolute value less than or equal to c interproducted with 2 to the minus j k tilde arc c gradient of psi 1 of arc c over 2 to the j. And psi, this function phi and hence psi 1 is fixed. And that just has, this is Schwartz, so this has just some supremum over it. And c, don't forget, c is between, where do I want to do it? It's between 2 to the j plus 3 and 2 to the j minus 1. Therefore, c times 2 to the minus j is restricted to some interval, and that's where it's 1/2 up to 8. So this term is also bounded. And what we end up getting is that this is just up to some constants, depending on phi and hence on psi and hence phi. And this h here is at most the alpha j. Because alpha j is the supremum over the Fourier transform of k in this range. Phew. So you do that same L2 adaptation as right here. And that just tells you that this thing is at most, well, there's the beta j coming from this term, and there's alpha j coming from this term. And you end up getting the square root as you got for the alpha j in the previous step times the the L2 norm of f. Great. And yeah, and that's the norm. Or that's Bourgain's lemma. Oops. Wonderful. Now you can get a corollary of this. And that is by just removing the projections. That was for one single j, right? Now, if I want to use the series, the sum of pj of k is equal to k in a suitable sense, then this is going to be taken by summing over all the j's. All right. Which we saw in this sort of thing, but we chose only high j's instead. Okay. Phew. Any questions on that? That was a bit terse, but it's I think it has all the details. Great. Okay, that was useful for high frequencies when we consider it S high. Let's actually now consider low frequencies. And let's get this bound. That turns out to be the high frequencies. We had a nice L2 bound. So the low frequencies are now going to have a good L1 bound. And to start us off, let's just warm up with a little bit of this simple inequality right here. So if I take sigma r to be the normalized spherical measure on a sphere of radius r, and I consider these convolutions. So I fix a integral function phi, and I look at the L1 dilations of its Fourier transform. The Fourier transform exists because phi is integral. Then it turns out if I take any of these dilations, I end up getting this bound in terms of the L1 norm of the original function. This is just following because sigma r is a probability measure. I'm not going to actually do much work to do this. How do we prove this? Well, we know that the L infinity norm of this, so dial is at most the L1 norm of the Fourier transform, which would be that's a 1. Times, of course, the Fourier transform of this buddy too. No, that's not what I wanted to say. Sorry, that's not what I wanted to say. What I actually meant was looking at just, I can get a nice L infinity bound for just this term right here. So and that is done by looking at the Fourier transform. in L1. And I use the intertwining property of the dilation operator now. That is just no, it's even sillier than that. Don't know why I keep trying to take the transform, Fourier transform. All right, finally, this is bounded L infinity norm of the Fourier transform, but it's an L1 dilation. Okay, so that is just the L infinity norm of t to the minus d of I dilate by t in L infinity. And so that is just t to the minus d times this L infinity norm. But that dilations don't affect the L infinity at all. So that disappears. And now it's just bounding the Fourier transform of the function in L infinity. And that, of course, was just less than or equal to the L1 norm of phi. Okay, that's just one part of it. How do I use that? Well, I'm going to say that as a result, this is actually the one function times that dilation involved with sigma r. And I can actually split that up. So that's less than or equal to the L infinity norm of this, which I've already estimated, times 1 convolved with sigma r. Then 1 is just the one function everywhere. And that's, of course, just that equals 1 because this is normalized to be a probability measure. And then this has the bounds of this from before. Great, that's a very simple bound. I mention that now because it's very simple, hugely flexible though. It's just relying on the spherical measure having probability measure really. But we actually need to use the fact that we have the spherical measure, and the fact it's not curvature this time that's an important property about it, but it's the dimensionality of the sphere. So what do I mean? Or the spherical measure. So we have the following property for the spherical measure. If you give me any ball in RD of radius r, so it's centered at any point x, then you actually have the following bound for the volume for the spherical measure of that ball. And it's bounded by the radius to the dimension -1. Okay. So the way you see that is that this is the unit sphere, of course. I take my unit sphere, and now if I take some ball with a small radius, that ends up giving me a small cap of radius r. And that cap has a d-1 volume about r to the d-1 up to some dimensional constants. Alternatively, I could also have a much bigger ball. And now it intersects the entire sphere. But the volume of the sphere is 1. So this volume of the orange intersection is at most 1, which is certainly much smaller than the radius dimension -1. So this bound is valid for all r, but it's most useful actually when r is small. Okay. When r is large, we really get that it's you can do something much better. But it does give us some improved bounds. So the previous bound, I didn't say this, but should have. This is quite good when I take a very big T. And now why does that relate to what we've been talking about? If I plug in the right this phi isn't the same as the previous phi, right? If I plug in the right version of it though, I'm looking at the right dilations of sigma r, and I'm showing that in L1, there's a lot of I can measure a lot of cancellation. Actually, sorry, this isn't cancellation. I can measure the fact that this is a very shallow average of the spherical measure. And now when t is very small, I can show that it's also quite small. And what is the thing? If I fixed my function phi, or its Fourier transform, equivalently, then when t is quite large, that should be a t there. When t is quite large, we had this was less than t to the 1 minus d. This function is looking very broad and shallow. But when t is quite small, it's very localized. It's looking quite like a delta mass. And so then in that case, you're very low. When t is small, you're localized sigma quite a lot. When t is large, you really smooth it out. Great, so let's show this. How do I do that? I'm going to start using the dimensionality of the sphere. So I take, I look at this, phi is Schwartz, so the Fourier transform is Schwartz. And in particular, that means that when I consider these dilations, I actually have the following pointwise bound automatically. That is t to the d over 1 plus t times absolute value of x. And that's to any power n. Now I plug this into that convolution. So that, oops. This is actually equal to, or sorry, is bounded by some constants depending on n. These are both non-negative or positive measures. So I get to just say that this is bounded by t to the d 1 plus t x minus y to the minus n d sigma of y. And now we cut up the sphere into a bunch of pieces and analyze it there. So this is actually over the sphere S. So define S naught to be the set of y and S, such that x minus y is at most some constant times t inverse. Maybe that constant's 10 if you prefer. And for j in n, we'll define this as the set of points in the sphere such that, let's just say less than or equal to there. And this is going to be 2 to the j minus 1 t inverse less than or equal to just less than x minus y up to 2 to the j t inverse for j and n. And we know, this is each of these is the intersection of the sphere with a ball of the given radius. For the top one, for S naught, it's a ball of radius t inverse. And for the SJs, it would be a ball of radius 2 to the j to the t times t inverse. And that's actually an annulus there, but we'll be able to cover these by the whole ball instead. And that doesn't lose too much for us. So let's write that out. Let's just say sigma of S naught is then at most t to the 1 minus d, and sigma of Sj is at most 2 to the j over t to the 1, oh, sorry, d minus 1. And we plug that into this expression here. So we had the integral over s, well, t to the d I can pull out. Now 1 plus t x minus y to the minus n. The sigma of y is actually equal to t to the d, the sum over j, 0 to infinity, the integral over sj. Of, 1 plus t x minus y to the minus n, the sigma of y. And, well, we defined our sets just to exactly offset this right here. On Sj, this is just 2 to the j. Sorry, 2 to the j. And so this is bounded by t to the d, the sum over j, and it'll be 1 plus 2 to the j to the minus n, but integrated against sj d sigma of j, which itself was, as we said, just bounded by some constant 2 to the j over t to the d minus 1. And now you see the factors of t cancel each other. So we have t times the sum over j equals 0 to infinity. And then I can bound this by 2 to the j. So minus 2jn times 2 to the j d minus 1. But if I just choose n to equal d, anything bigger than d minus 1, this of course is summable. And we end up getting, that's at most t. All right, this is not quite the best thing we can hope for. It turns out you can actually improve this to depend on the point and actually get this better bound right here, where it depends on the point x. Let's go back and do that then. Refines our analysis. Okay, how do you do that? There's a nice little trick in this. First off, our sets Sj, S naught, they're going to be the same as before. But we have this extra localizing factor. It turns out that Sj of, I can look at Sj of x, right? So these points were actually implicitly, these sets are implicitly depending on x, even though I didn't keep too good track of it, or any track of it really. But we have this nice effect that Sj of x is empty, implies that x is less than or equal to, oh, sorry, the other way around. Sj of x is empty for x sufficiently large. That's greater than, so 2 to the j plus 1 t plus 1. All right, so I've cut these little caps up. I've cut the sphere up into these different regions, but most of them are actually empty. And, I mean, only finally many of them are not empty. Okay, and so that ends up giving us this localization where I get to multiply this whole thing times the characteristic function of that ball. And you get to use that characteristic function, say, of the unit ball. Well, you can bound that by just 1 over 1 plus x to the n, m, for all m. All right, by scaling, that also means that 1 of b to the j plus 1 t plus 1 is bounded by, this is at x, it's bounded by 2 to the j plus 1 t plus 1 all over 1 plus x to the m. That's not obvious to see, but I'll leave that calculation for you to convince yourself. It's just you're just dilating out that ball. But we still can use, we get to use this. And now you use the same decomposition as before, but I could split this integral, this sum, sorry. Two pieces. The sum over j goes from 0 to log of t, plus the sum of, all j greater than log t. I'm going to call this sum the nearby parts and this sum the distant parts. Okay, so let me write out what the nearby part would be. I'm looking at the sum over j equals 0 to log of t, excuse me, the integral over sj of x, 1 plus t x minus y minus n d signum of y. And these were localized, right, by that 1b 2 to the j plus 1 t plus 1 of x. So this is less than, as before, this is log base 2, by the way, the following thing. So I get this factor is going to be 2 to the minus j, so that the whole thing in parentheses is 2 to the minus j n. The volume of the sj of x is again at most 2 to the j d minus 1, and times t to the 1 minus d, so you have an inverse there. And then I wedge in that bound, the 1 over, sorry, not the 1. It's going to be it will be the fact that I've chosen j up to log of t means that this thing is always, say, less than or equal to 3. And so I actually just have this times the ball radius 3 at x. And then I just get to use, this is that bound, the 1 over 1 plus x to the m for all m. And now the distant part is similar. I've got sum over j greater than log of t. This integral sj of x, 1 plus t x minus y to the minus n. All right, and with this factor, which I get to replace by an expression like this. But the way you handle that is you end up saying, all right, I'm going to throw in a little bit more. I'm going to take n here a bit bigger to cancel out the m that would come from there. So this is sj of x, and that's again 2 to the minus j n, this is d signum of y, and that's going to be 2 to the j plus 1 t plus 1 over 1 plus x to the m. So just choose n equal to something like m plus d plus 1. I don't know. And what you find out is this gives you, oh wait, to the t. There's an inverse here, sorry. These are all inverses, that's the, great. And yeah, so I end up having that the above is at most degree log t 2 to the minus j n to the j d minus 1 to t d minus 1 and yeah, and 2 to the j plus, well, to the j t inverse to the m 1 plus x to the m. This 1 is going to be swallowed up because the j's are sufficiently large. And the, yeah, this factor of 2 to the m, I'm just absorbing in some implicit constant over here. Right, so if I choose n large enough, I'll get a factor of t to the d minus 1 coming out, as well as this factor. I just need to be able to sum up this series. But the fact that I've chosen j larger than log of t means that this is actually a positive power of 2. This is at least 2 to the, yeah, sorry, this as j increases, this is at least 1, and then it's 4 and so on, right? This, I guess I should just say it's just 2 to the j minus log of t times m. The log of t is I'm doing all the ones bigger than log of t. So this thing is in fact summable, and you get that this is at most t to the d minus 1 plus x to the minus m. Oh, sorry, that's a minus sign right there, which is the bound I wanted. And that depends very much on m, the dimension, and the n that I chose to offset the m. But yeah. Okay, that maybe is a little scrambled, but are there any questions about how to do this? There's a nice analysis of breaking up the sphere into a bunch of pieces and applying the dimensionality at each stage of it. Moving forward, then, we've got this lemma. And this is going to give us a nice comparison with the Hardy-Littlewood maximal function. And so what we find out is that the low frequency parts of the spherical averages is dominated by the Hardy-Littlewood maximal function. In fact, so remember that's S, oh, that should say S high. So S R high, or S1 high, was defined so that it's A1 and then P greater than, I wanted to say P greater than J. So this would be that J. Oh, yeah. And this is actually a pointwise estimate. It's not an L1, it's not an L2, so on. It's a pointwise estimate by that lemma. And the way we get to apply that lemma is there is, so for any approximation of the identity, you get to compare those to the Hardy-Littlewood maximal function over balls by an argument that appears in Stein singular integrals. It's not too difficult an argument, but it takes us a bit aside, so I won't really go into it. I'll give you some intuition for why it works. Basically, you can think of as you have an approximation of the identity that is, like, say, monotonically decreasing as you go away from the origin, radially decreasing. Then what you have is you have some profile that looks like this. And you can just think about it as the layer cake decomposition. I've got some ball average like this at that scale, then some ball average at twice that scale, and then 4 times that scale, and so on. You can add it up, or you can dominate it by this sort of geometric series of Hardy-Littlewood averages and sum it up to get something that dominates the function, the orange function. Now, the right way to do this is actually to do it by level sets, and then you get a more general condition. But all you have to do is verify that the following holds. When I integrate over all these points on X, I get that this is bounded by T. And that follows immediately because we had the bound of, we had that this thing pointwise is at most T over 1 plus X to the M for arbitrarily large M. And so you can just integrate over all the X to do that. Okay, now we're finally almost there, getting to Bourgain's restricted weak type inequality. Just to remind you what it is, we want to prove this level set estimate. This is for, so for F, a measurable function, measurable set in RD. Right, and for all positive alpha. So the proof of this is really quite nice. Yeah, it's one of my favorites. So before we had the 2 inequalities before. Let me just rewrite them for us. We have, okay, let me introduce some notation here to make our lives easier. I'm going to add a star to the bottom of an operator, and that means I'm taking the supremum over all R's. And so if I have S star of F at X, that is by definition the sup over all positive R of S R F of X in absolute value. Now, when I do something like I have high here, that's the same as putting high here. And if I had instead low, it's the same as well, okay? Right, so before we proved 2 estimates, one on L2, we showed that S star high of F in L2 was at most 2 to the J 1 minus D over 2 times the L2 norm of F. I'll call this 2, and I'll call the other one 1. Should have written it first. All right, S star low on F. Well, okay, I didn't prove this yet, but I'll tell you how to in just a minute. This is at most in L1 infinity. It's at most 2 to the J times the L1 norm of F. So what do I mean by that? I have this pointwise comparison for the Hardy-Littlewood maximal function, right? Oh, that shouldn't have said high. That should have said low, obviously. I'm talking about low frequencies there. Blah. Low. And low is all less than or equal to J. Right, okay, so now that I have this bound, I have S star of low, F of X. If it's greater, if I'm looking at this set where it's greater than alpha, all the points X that are greater than alpha, well, that's at most where MF, sorry, I should say 2 to the J, MF of X is greater than alpha, but really up to some constant and in measure. And I know that, okay, so that's equal to measure of F the measure of maximal function greater than 2 to the j minus j alpha up to some constants by just moving the 2 to the j over. And the Hardy-Littlewood theorem says that this thing is at most 2 to the minus j alpha inverse the L1 norm of f. And that is, of course, just 2 to the j alpha inverse of f on L1. This is good. Yeah, so we get, what I should really say here is that the L1 norm of S low, maximal function, greater than alpha is at most some constant I don't care too much about, alpha inverse to the j f in L1. Brilliant. This, by the Chebyshev-Markov inequality, actually also tells us a level set estimate. It tells us that the high part, satisfies this. This is greater than alpha. Then on L2, it's at most some constant I don't care about. 2 to the j, 2 minus d, and the L2 norm of f squared, and this is alpha to the minus 2. So let's combine these. And the cool trick here is the very simple observation that the LP norm of the characteristic function of a set is actually just the Lebesgue measure of that set. The LP norm to the pth power is actually just the Lebesgue measure of the set, right? You see that immediately by just writing down this definition. This is the integral of 1 of f to the p, but that's a non-negative function. So it's just equal to the integral of 1 of f to the p as well. But that's also just, it's either 1 or 0, so that p doesn't matter. And that's just the size of f. So what does that mean if I plug in my f is equal to 1 of f here? So f is defined to be the characteristic function of some set f. That just means I have this at f, and I have this. Okay, and now the game is going to be to choose the j to optimize this inequality. And why do we want to do that? Because, quite simply, the triangle inequality, tells us that this is at most this sum. This is every point. And therefore, when you look at the level sets, I'll look at S star f of x greater than alpha. This is at most S low greater than alpha over 2 plus the high part greater than alpha over 2. And I apply those two bounds from before. So that's at most up to some constants, alpha to the minus 1, 2 to the j, the volume of f of that set, plus alpha to the minus 2, 2 to the minus j d minus 2, volume of the set f. And so we choose these two to be equal. We choose a j, so these two are basically equal, right? I want to say alpha inverse 2 to the j is up to some constants, alpha to the minus 2, 2 to the minus j t minus 2. When you do that, of course, you're going to get alpha is about 2 to the, okay, that's j 2 minus d minus 1. There's 2 to the j, j minus j times d minus 1. And now, okay, that's the same as taking alpha to be about 2 to the minus j, alpha to the 1 over d minus 1 to be about 2 to the minus j. Or in other words, 2 to the j is about alpha to the minus 1 over d minus 1. Let's plug that back in here. We know both sides are optimal or optimized. So this is all together at most alpha inverse times alpha to the minus 1 over d minus 1 times the volume of F. But this is then alpha to the minus d minus 1 over d minus 1 minus 1 over d minus 1 times the volume of F, which is of course just alpha to the minus d over d minus 1, the volume of F. And that is what we wanted to show. Phew, bit of a race to the end there. Were there any questions? Any part that seemed unclear? All right, thank you very much then. I will continue next time by actually starting to talk about the discrete spherical averages and the discrete spherical maximal function.